Screen share is loaded there. All right, so before we get started today, a couple of things. A, I don't feel well and my throat is sore, so I'm going to get through this as fast as I possibly can. B, I'm going to be uploading a couple of homework assignments this weekend. Actually, probably three. One having to do with capacitive sensing, one having to do with piezo-resistive sensing, and one having to do with our topic today, piezoelectric sensing. I would expect these homework assignments to be very short, 2 to 3 problems at the absolute max, just so that I can have a kind of accelerated due date so that you guys can work on them and turn them in prior to your exam, which will be next Friday. Okay, so just giving you a heads up. I think sum total, I plan on giving you guys like 7 problems total to work in the next week-ish. All right. And over our brief break here, one day, I will also be working on compiling a list of theory type questions that I might ask you on the in-class portion of your exam, which, to remind you again, is next Friday, because I believe I said I'd do that in our last class meeting. Okay. Right. Today we are going to be talking about piezoelectric sensing. So to understand piezoelectric sensing, we must first understand the piezoelectric effect. There are 2 parts of the piezoelectric effect. First, we have the direct effect, which put simply says that when a piezoelectric material is mechanically deformed, so meaning it undergoes some sort of strain, an electric field is generated across the material. And the indirect effect is the exact opposite, or the inverse effect. When an electric field is applied across a piezoelectric material, it will undergo mechanical deformation. Okay, so this can sound fairly similar to the piezo-resistive effect, okay? So in the piezo-resistive effect, when we stress a material, we see a change in the material's electrical resistance, right? Here, we are stressing a material and we see a self-generated signal, effectively, a electric field, and electric field multiplied by the length over which the electric field is applied gives us effectively a voltage, okay? So 2 different things, but they can sound kind of similar. So let's talk about differences here. piezoelectricity and piezo resistivity. Sorry, making sure I'm spelling that right. So the first main difference is that while all materials exhibit piezoresistivity, only some materials exhibit piezoelectricity. So in order for a material to be considered a piezoelectric material, there are really two criterion that need to be satisfied. First, the material needs to contain in its structure polar bonds, okay? So let's consider silicon dioxide or quartz crystal. Okay. So if we have quartz crystal, if we were to slice quartz crystal and look at it, in one of its crystal planes, and it's hard to identify the particular plane because quartz crystal doesn't have simple cleavage planes like silicon does, so we can't just say the 110, all that kind of good stuff. But so let's say this black blob represents a silicon atom. This red over here will be an oxygen atom. Here we have a silicon atom. Here we have a silicon atom. And then we have another oxygen atom like so. So in quartz crystal, the silicon atoms, sorry, don't know why my pointer's doing that, are weakly positively charged. Hold on just a second. Close. It's just going to keep on making that noise and giving me that error if I don't do this. No. So the silicon atoms are weakly positive and the oxygen atoms are weakly negative. And so effectively, these are covalent bonds, but the oxygen is a little bit more greedy in its need for electrons than silicon is for its need, okay? So we have polarized bonds where we have some weak positive charge on the silicon atoms and some weak negative charge on the oxygen atoms, okay? So we have a material that contains polarized bonds, which is one of the criterion. And the other criterion is that our material cannot have point symmetry, okay? So what that means is that directly across from the silicon atom can't be another silicon atom, and directly across from the oxygen atom can't be another oxygen atom. And I'll show you why this is important, okay? So if the drawing that I have here represents our crystal in an uncompressed state, where is the center of positive charge?
Somewhere in between the structures.
Should be directly in the middle. Where would the center of negative charge be? The same place, right? But now let's look at what happens if we were to squeeze this structure, right? So if we squeeze this structure, the topmost silicon atom is going to move down, and the bottom two silicon atoms are going to be pushed left and right. Okay, so we're going to have something like this. So here's silicon. Here's an oxygen. Here's an oxygen. Here's a silicon. Here's a silicon. Here's an oxygen. And so we should see that the center of positive charge, which I'm going to put in black, is actually going to wind up shifting slightly, right? So it's going to be slightly below that central point of the hexagonal shape. And the center of negative charge is going to be slightly above the center point of that hexagonal shape, so that we have charge accumulation below and positive charge accumulated on the bottom and negative charge accumulated on top. Well, what happens when we have separation of charge? Creates an electric field, right? Which is exactly what we would expect in a piezoelectric material. Mechanical deformation results in the formation of an electric field oriented from the positive charge region to the negative charge region, right? So we're going to see some E field in the up direction when we compress this crystal. Now, counter to this effectively, so let's consider if we had a material with this structure. In the uncompressed state, the center of positive charge is the center of the diamond shape. The center of negative charge is also the center of the diamond shape. What happens when we compress this crystal? The center of the positive charge is still in the middle, and the center of the negative charge is still in the middle, because we don't have any movement of the point of average charge, or the centroid of charge. We're not going to see a piezoelectric effect. Okay, so we need both polar bonding to happen, and we need to have asymmetry. Without those two things, we will not have a piezoelectric material. Okay. Now, quartz is probably the most common piezoelectric material. It's been around, well, its use as a piezoelectric material has been around forever. In fact, how many of you here are wearing a digital watch? I know I am. About half of us. So about half of us have a quartz crystal on our person at this exact moment, right? Most digital watches, I say most, it's really all digital watches, use what's called a quartz crystal resonator that resonates at a very specific frequency. Let's call it 32 kilohertz, but it's not really 32 kilohertz. It's whatever 2 to the however many powers gets to the ballpark of 32,000 it is. And it's mechanically tuned, so the crystal is trimmed to have that particular resonant frequency, and it uses that exact number of oscillations per second to tell your watch how long a second is, right? Quartz crystals are also used in not like a regular cigarette lighter, but like a grill lighter. So a regular standard cigarette lighter effectively uses a flint where it's friction against a particular type of metal that generates sparks, lights the gas, and all that kind of stuff. In a grill lighter, you have that trigger, yeah. And so what that trigger is it's a spring that's storing energy, and then once you pull it down far enough, a hammer releases and strikes a piezoelectric crystal. And that piezoelectric crystal has leads that run up the length of the barrel of your lighter. And concentric to those leads is a gas line. So when you strike that crystal with that hammer, it generates a voltage or an electric field across the distance of those two leads, which in turn creates a spark. And when that spark is in the presence of a combustible fuel, you get fire at the end of it. It's also how, for those of you that have barbecue grills at home and it has a push button igniter, that's a piezoelectric crystal. They're all around us. Okay. Been used for many, many, many years.
Why these lighters are not that common because of the cost, like compared to the liquid lighter?
So it's working in conjunction with the liquid. So all the piezoelectric crystal is able to do is provide the spark. It's an alternative means of combustion. So we might be having a language barrier type issue, so I'm going to show you a picture.
The reason they use that cylindrical flint for your internal wheels or something similar is it's long stem light. So if you're trying to start a spark way down here, but you're supposed to plug this way up here at the tip, that spark has to travel a whole lot further, and then you have to come up with some sort of weird mechanism that down here at the handle that causes it to guide the tip.
Yeah, so this is the type of lighter that I'm talking about in particular, right? So if we were to take this thing apart, this trigger is acting on a spring, which is storing energy, and it's literally a little piston that once you pull it far enough, it gets released and it smacks into this crystal. The crystal has electrodes on both sides of it, and wires that literally run all the way down the length of the barrel. And then in the middle of the barrel is a gas line from the reservoir, which is down here, out to the top. So when you let gas release down that length of line and you provide a spark from the piezoelectric crystal, you have fire coming out this long end. Whereas a traditional cigarette lighter with a flint actually cheap Bic lighter. I don't want to get Zippos and fancy things like that. So these lighters, the spark is generated by friction from that wheel rubbing against a piece of metal. So there's no need to pass that spark a long distance down the length of that barrel, which is what Stephen was suggesting. So, all right. Excuse me.
Sorry, please can you repeat that statement?
I'm sorry, what?
The piezoelectric material, like you said, it's going to combine to it needs to be polar bonding.
Okay, so it needs to have polar bonding as well as point asymmetry, I guess. So not point symmetry, where what I mean by point symmetry is if we went from this point here to this centroid, the thing directly across from it isn't the same material. All right, so there are a lot of man-made piezoelectric materials. Okay, one of the most common is PZT, or lead zirconate titanate. Let me just write this down over here. PZT. There are multiple different formulations. PZT4, PZT5A are both widely used piezoelectric. The important part about these, they're ceramic materials. Okay, so typically speaking, they don't really have that asymmetry that's necessary. And so how we force that asymmetry in this type of material is we subject it to a strong electric field to line up all of the dipole moments. And if we keep it in that strong electric field for long enough, effectively its grain boundaries will all align and it will contain some residual piezoelectricity. So this is very similar to how we magnetize materials, right? I don't know how familiar you all are with, BH curves and magnetization. But effectively, if you have a ferroelectric material, it has domains that have magnetic dipole moments in particular directions, and they're all randomly oriented, right? If you subject that material to a strong external magnetic field, all of those magnetic dipole moments tend to line up with each other. Well, there's a certain point called saturation where increasing the field strength doesn't align the dipole moments anymore, because you can only get parallel. That's the best you could possibly get. So any external field beyond that doesn't really do anything. Well, when you back off in that BH curve, effectively you'll see the material, a ferroelectric material, exhibits residual magnetization. Well, this is the same thing that's happening in these ceramic piezoelectric materials, except that you have a residual electric field instead of a residual magnetic field. You do have to be careful though, because much like in magnets, if you were to increase the temperature of the material beyond its Curie temperature, it would lose that residual magnetization, effectively resetting the grain boundaries and all that kind of good stuff. So that process is what's called poling, P-O-L-I-N-G, because it's establishing a net dipole moment in the crystal. And that is something that's very common in man-made ceramic piezoelectric materials. Yeah. All right, so let's talk about our second difference here. So I'm going to use B. So piezoelectric materials are self-generating. So what I mean by that specifically is, in order for us to determine some change in piezoresistivity, we have to apply either a bias voltage or a bias current in order for us to measure it. We don't have to do the same thing for a piezoelectric material. Okay, it generates its own output signal. So that applied strain generates a voltage, or an applied voltage generates a strain, right? So we don't have to use bias circuitry and all that kind of stuff. So inherently, our DC power consumption for our piezo element by itself is zero, because it generates its own power. Or really, it's a transducer, so it converts mechanical energy into electrical energy, or vice versa, right? Our last difference that we're going to talk about is that piezoelectric materials cannot be used to measure DC quantities. I wish I had thought about buying a simple piezoelectric disc so that I could show you guys this, and it would give me an excuse to hit things with a hammer. But the piezoelectric effect, we're going to find out mathematically in our model here in a moment, is all related to the rate of change. So we need to have a changing stress in order to generate an output voltage, or we need to have a changing voltage in order to generate mechanical stress in our crystal, right? So we can't simply, if we had an accelerometer, so a cantilever beam that had a piezoelectric sensor to measure the strain, when we depress our cantilever, that change is going to give us some signal, but the continued application of that force is not going to continue to generate a signal. So we're going to see a transient effectively. There are plenty of YouTube videos you can literally watch of people taking a piezoelectric crystal with some wires running off of it, connecting it to a voltmeter and then whacking said crystal with a hammer and looking at the voltage output. And you'll see that the voltage output depends on the force at which you hit it, which in turn is, how quickly you're applying that strength. So the faster you whack it, the larger the voltage that you get. This is part of the reason why piezoelectric materials make such great reference oscillators. If you have a specified voltage that you're applying across it with a specified frequency, then it resonates at that particular frequency. For you guys that did your undergraduates here, you saw this way back in engineering 121 with those little speakers that you connected to your Arduinos. Those were all piezo speakers. And so you applied a square wave voltage to them. So either voltage on, voltage off at a specific frequency, and the output you heard was that crystal resonating and pushing air through that little circular aperture in the middle of the housing, generate sound. So, all right, so let's get to our mathematical relationships here, okay? So we've talked about the differences in piezoelectricity and piezoresistivity. Just as a heads up, that's a great test question. So mathematically, I wrote piezoresistive when I meant piezoelectric. My apologies. So our first relationship here, we're going to have D. So this is the electric displacement vector or the electric flux density. Okay, so it's related to electric field, will be equal to epsilon times E. So that's the standard relationship that you would expect to see in a non-piezoelectric material. It's one of Maxwell's equations. D is equal to epsilon E. But in a piezoelectric material, we also have lowercase e multiplied by S. So this is the electric displacement. Also known as, I usually use those kinds of brackets for units, so I don't want to do that. And it is measured in coulombs per meter squared. This epsilon, actually, hold on. Now I'm going to confuse myself. I'm going to make that a large script E, and I'll explain why in a moment. Sorry, Sam. Yeah, so we have a little epsilon that looks suspiciously similar to a large script E, but this little epsilon represents the permittivity of the material, which is measured usually in farads per meter or farads per centimeter, farads per micron, farads per unit length. This large script E is the electric field measured in volts per meter typically. This lowercase e is the piezoelectric coefficient, which has units of coulombs per meter squared. And capital S here is our mechanical strength. So this is the mathematical description of the direct effect of piezoelectricity. And we know strain is unitless. And now you'll see why I erased that capital E and replaced it with a script E. Inverse relationship T stress is equal to Young's modulus capital E times strain minus lowercase e times script E. So here we have stress, which is in newtons per meter squared or pascals, Young's modulus, in newtons per meter squared or pascals, strain and then our piezoelectric coefficient and our electric field. So this is how these constituent equations are given in the official textbook for this class, Practical MEMS by Dr. Vili Kajakari. In a reference textbook that I am using to supplement things, they're expressed in a slightly different way, where the piezoelectric coefficient has different units and it uses what's called a compliance matrix. I didn't have time to really go through and unpack how to convert from one to the other, so this is what we are going to be using. I just want you to be aware that it can be expressed in a slightly different form. Okay, if you were to look at a different textbook. All right, so piezoelectric materials are by definition anisotropic materials because they have to be polarized and they have to have asymmetry. Okay, so really these constituent equations are large matrix or tensor equations. That being said, the overwhelming majority of piezoelectric sensors are going to fall into one of two cases, either a longitudinal transducer or a transverse transducer. So we can simplify this math into something of a more closed form solution. Okay. So let's look first at the case of a longitudinal transducer. So I'm going to start with my piezo element, which I'm going to put this structure in blue here. So this is my piezoelectric material. My piezoelectric material is going to be sandwiched in between two electrodes because I need to be able to send my generated electric field somewhere else. So this is the top electrode. And the bottom electrode. So I'm going to ask you what I hope is an obvious question, but what does this thing look like right now? A capacitor, absolutely, yes. I'm going to connect to this device a voltmeter so that we can figure out what the output voltage is. And I'm going to define some critical dimensions here. So let's call this positive H/2. Let's call this negative H/2 because we're going to be doing some integration. So these are going to be our boundaries. I am going to define a coordinate system here. So I'm going to call this up the 3 direction and out the 1 direction. And so if I apply a force in the 3 direction, I should observe a field in the 3 direction as well for a longitudinal transducer, where this, sorry, B is for magnetic field. I want electric displacement. So we have some field D3. Okay. So in this particular configuration, the electric displacement in the 3 direction is given by epsilon, the permittivity of the piezoelectric material, multiplied by E3 plus E33, our piezoelectric coefficient, times S3, our applied strain, or epsilon E3 plus E33 times the derivative of U3 with respect to capital X3. And I'm going to unpack what the heck that thing means there. Okay. So this term, U3 as a function of X3, is the material displacement in the 3 direction at location. Let me erase that so it looks more like I know how to spell. X3. So effectively, it's a measure of the deformation of the crystal when we have some induced electric field or displacement field, or vice versa, right? Our piezoelectric coefficient effectively couples our stress strain relationship to our electric flux density, electric field relationship, so it works both ways. But anyway, so just telling you what the things are as we do the math here. All right, so what we're going to do is we're going to integrate this guy. We're going to integrate both sides across the entire thickness of the crystal. So we're going to have the integral from negative h over 2 to positive h over 2 of D3, D capital X3. This will be equal to the integral from negative h over 2, positive h over 2 of epsilon E3, D capital X3, plus the integral from negative h over 2 to positive h over 2 of E33. Sorry, that shouldn't be an X, that should be a 3. Like so. So these two guys effectively cancel each other out, so we'll unpack that in a moment. But since our displacement vector is a constant across the thickness of the crystal, and our electric field is a constant across the thickness of the crystal, and our permittivity is a constant across the thickness of the crystal. These first integrals are effectively just multiplying by the thickness of the crystal, h, right? So we're going to have D3 times h will be equal to epsilon E3 times h. And now I'm going to pull the E33 term. So that's our anisotropic piezoelectric coefficient in the 3 direction. And when I do this integral, I'm integrating du3 from negative H2 to H2. And so this is going to look like U3 at location H2 minus U3 at location negative H over 2. What does that represent? Deformation of the crystal, right? So however much this crystal deforms, plus this term right here, gives us our displacement field. Okay, so now we're going to do a couple of things. All right, so our electric field multiplied by the thickness of the crystal is going to give us the voltage drop across the crystal. Because electric field times distance is voltage, right? So we can say that V3H will be equal to epsilon V plus E33. Sorry, that should be U, not mu. I don't want to confuse things. So the displacement at the top of the piezo material minus the displacement at the bottom of the piezo material. Now we are going to multiply both sides by our plate area, which I'm going to call A3, and divide both sides by H. So go away thing. So we're going to wind up having A3 D3 equal to epsilon A3 over H times V plus E33 A3 over H mu 3 H at H over 2 minus mu 3 at negative H over 2. All right. So let's look at a couple of things here. Okay. The thing that's probably a little bit hopefully obvious, we have epsilon times area divided by height. That's capacitance. EA over D, where D is the distance separating our plates, which in this case is just H. So this term right here is just the nominal capacitance of our piezo element, all right? The A3 over D3 thing is a little bit harder to understand, but we can think about it in a couple of ways, right? So A3 times D3 is going to capacitance times voltage plus this other term. Well, what's capacitance times voltage? Charge, right? And if we looked at the units of A3 and D3, that is coulombs per meter squared times meter squared gives us coulombs, so it is charge. So I'm going to call this thing here Q. So why this is important is because if I take the derivative of Q with respect to time, I get something I can measure, current, right? So we can say then that I, which is the change in current with respect to time, will be, let me get to the right point in my notes here so I don't mess things up. C dV by dt plus E33 A3 over H, all of those are constant, times the time derivative of U3 H over 2 minus, close that, U3 negative H over 2. So the current that can be output by this thing is dependent, or really I should say actually is proportional to the velocity of the deformation, or how quickly we deform it, right? Because that's what the derivative of the U of 3 represents. If U of 3 is a distance representing the amount of deformation, the time derivative of that is the velocity at which that deformation occurs. So in the frequency domain, just to make the math easier, these derivatives are simply multiplying by. So what we'll have is a current I that is equal to SCV plus SE33 A3 over H times U3 of, or at H over 2. I want to be very clear that this is not multiplication. U3 is a function of position. Minus U3 at negative H over 2. So the last thing that we can do here is we can say that if our strain is constant, across the thickness of our piezo material, then U3 at H over 2 minus U3 at negative H over 2 represents the change in H. Right? So the amount of the change, and since we have the change in H divided by H, that is the strain in the 3 direction.
Can you please explain the previous slide? How does the SK?
Okay. So this S right here is the Laplacian operator S. So when we take a derivative in the frequency domain, it's the same as multiplying by S. We actually talked about this before the break when I introduced this previously. Okay. So for a steady state sinusoidal system, S is J omega. Is this ringing a bell and all this kind of stuff? It's that same S. So just so that we don't have derivatives with respect to time everywhere, and we're going to see, think of this S as frequency. So it is representing effectively the rate of change. All right. When we do a little bit of playing around with this math with our measurement circuits, we are going to find that the frequency dependency winds up going away. But anyway. All right. So if the strain is constant across the thickness of the piezo material, then we get the relationship I is equal to SCV plus S E33 A3 capital S3. We're going to call this part simple AC current due to the presence of the capacitance. And this part is going to be the motional current. It's related to the applied strain. Okay. So we have a similar relationship here as to what we saw with capacitive sensing. That being said, the magnitude of the currents in piezoelectric sensing is going to be significantly smaller because the deformations that are experienced are very, very small. Right. Okay. So that's the math behind the response of a longitudinal transducer. We're going to go through the transverse transducer very quickly because it's effectively the same equation, but our directions are different. Let me see if I have any lozenges left in my pocket. Yeah. All right. All right, so for transverse transducers, we have a very similar situation, except that our applied force is going to be along the length of our piezo material. So I'm going to try to draw this relatively quickly. All of the parts are effectively going to be the same, so I'm not going to label things for the sake of time. So we have our piezo material in the middle, sandwiched between two electrodes. This is effectively just our measurement tool to see what's going on here. This is still the 3 direction. This is still going to be the 1 direction. If I apply a force in the 1 direction, I can observe a, that's not the same color. Field in the 3 direction caused by the transverse piezoelectric coefficient E31. Okay. So in this configuration, D3 will be epsilon times E3 plus lowercase e31 times S1, or epsilon E3 plus lowercase e31 times the derivative of U1 with respect to X1. Oh, and I did not define my boundaries. We're going to call this negative L over 2 and this positive L over 2. I apologize for that. Where U1 as a function of X1 is the material displacement in the 1 direction at the X1 location. All right. This equation is effectively the exact same thing as we saw a moment ago. The only difference in derivation is we would be integrating along the X1 direction, so integrating along the length of our piezo material. And in doing so, we would find, that was very loud, that our current is going to be SCB, so we're going to have some term that's dependent on the self-capacitance of our piezo material times SE31 A3 over L. Let's see, this should be U1 at L over 2 minus U1 at negative L over 2. And under the same situation, so if our strain in the 1 direction is constant across the length of the crystal, or if we're going to treat it like the strain is constant because we don't want to figure out what the strain is everywhere, we can say that I is equal to SCV plus SE31 A3 S1. So exact same equation as we had before, except that we use the transverse piezoelectric coefficient when the strain is applied in the transverse direction. If you wanted to derive it, the steps are literally the exact same. All right, so now let's talk about measurement schemes, and then we're going to be done. First scheme that we're going to look at is, let's do the transimpedance amplifier first, okay? So effectively, we're measuring the current and converting it into a voltage. So let's say we're going to use, let me move this down so that I have enough space to put my impedance for my transimpedance amplifier. So I have an op amp. Do you guys that didn't do electrical engineering, do you guys know what op amp or how they work at all? An operational amplifier? Okay. I will very briefly describe the rules for op amps for you guys. So let me draw this thing real quick. Is understanding at least one small aspect of the behavior here. Is going to be critical to understanding where one of the terms goes. So this is our piezo element that'll be subjected to some amount of stress. And then just for argument's sake, that's going to be the direction of our output current. All that would change if it were the other direction would be the sign at the end, which isn't a big deal. Okay. So 2-minute crash course in op amps. Let me go a couple of pages ahead here real quick. All right. So this thing right here is an op amp. This is the non-inverting input terminal. This is the inverting input terminal. And this is the output terminal. This is an active device, which means technically it also has power supply connections as well. But from a circuit analysis perspective, we ignore them because they don't actually change the model at all. We just know that this device requires external power in order to provide amplification, okay? This device has a very large, let me do this in red. Input impedance. So depending on the type of transistors that are used to construct the device, if it's BJT transistors, the input impedance is on the order of mega ohms. If it's MOSFET transistors, the input impedance is on the order of tera ohms. So very, very large input impedance. So large that we're going to consider it effectively infinite for the overwhelming majority of applications. The output resistance of this amplifier is very small, typically on the order of single-digit ohms or less. So for our case, we're just going to call it 0 to make our life easier. And then we have a voltage gain, AV, that is very, very large, okay? Typical open, or I guess I should call this AVOL because it's our open loop voltage gain right now. EE people's eyes are glazing over, it's okay. This open loop voltage gain is typically on the order of a few 100,000 volts per volts. Okay, now let me go back a couple of pages here. All right. So the amplifier that we are using is in a negative feedback configuration. I can say that I have negative feedback because the inverting input terminal right here is connected to our output terminal by some impedance, which in this case is just going to be R in parallel with the impedance of the capacitor, okay? So in a negative feedback configuration, the gain of our amplifier is defined by that feedback loop. Okay, so the open loop gain isn't going to show up in any of our equations. Okay, so let me write some things down. Go back over here real quick. So let me do this in gray. So if we have some impedance Z connected between the inverting input and the output, this is negative feedback. This is used extensively in electronic circuits, control systems, all that kind of good stuff. If instead we had an impedance connected between the the non-inverting input and the output, this would be positive feedback. Positive feedback is only good for making oscillators, as far as we are concerned. Okay. Effectively, you have an unstable system to where a small increase in your signal level causes a large increase in the output, and then it winds up ringing back and forth between the power supply voltage levels. Doesn't pertain to what we are doing, just wanted to point it out in case you had questions. All right, so for negative feedback systems, we can say that two things are true. The voltage at the inverting input is going to be the same as the voltage at the non-inverting input. And we can say that the current flowing into the op-amps terminals is 0 amps. So this is because the extremely large voltage gain in a negative feedback configuration makes the differential voltage, the voltage that's measured between the non-inverting input terminal and the inverting input terminal, effectively 0. It's not truly 0. It really winds up being somewhere on the ballpark of a few microvolts, but it's close enough to 0 for us to not care. And no current can flow into or out of the input terminals of the op-amp because of the extremely large input impedance. Okay, so it took me a little bit over 2 minutes, but this is very, very basically how op-amps work. For those of you who had me for circuits 2, you're frustrated that it took me 4 days to get to this point. All right, so let's go back. Okay, so I'm going to label a couple of things here so we can figure out what's going on. This current is 0 amps, and this current is 0 amps because we know that no current can flow into the input terminals of the op-amp because of its very large input resistance. Since this voltage is 0 volts because it's connected to ground, this voltage at this node right here must also be 0 volts because the voltage present at the inverting input terminal has to be the same as the voltage present at the non-inverting input terminal for a negative feedback ideal op-amp, and it'll be very close to 0 for a real op-amp. Okay, So now that the op amp stuff is out of the way, let's talk about how this thing behaves. So effectively, that resistor in parallel with that capacitor converts the current that is output of the piezo material into a voltage, okay? So that's why it's a trans impedance amplifier. It converts current to voltage using impedance. So our current here well, let me just write it not as approximately equal, is going to be IAC plus I motional, right? Since the AC part of this current is proportional to the voltage drop across the piezo material, and the voltage drop across the piezo material is 0 because both sides are effectively grounded, this part goes away. And so we're only going to see our motional current get converted into an output signal voltage, which is awfully convenient because that's the part that is proportional to the applied stress, the applied strain, okay? So what we will find is that our output voltage here, V out, will be equal to negative I motional multiplied by R in parallel with 1 over SC, where the C here is the C in the feedback loop and not the C of the piezo material, which I'm going to call this CL just so there's no possibility of confusion. Okay. So for frequencies where omega is much greater than 1 over RC L, okay, our output voltage will simplify or approximate I motional divided by SC. Since our motional current is also dependent on frequency, we're going to have negative SE A times our strain, where I'm intentionally not putting in my subscripts here because I want it to be applicable for everything. So I don't want it just in a 1 direction or just in a 3 direction. E, lowercase e here is whatever piezoelectric coefficient we need. A is the area of our plate. And S is the strain in whatever direction we're looking at, divided by S, sorry, this should be CL. These two S's cancel each other out, and we effectively see that our output voltage is proportional to our applied strain, independent of frequency, which is exactly what you should expect. Like I said, if we hit it with a hammer, the amount of strain causes the voltage to get larger or smaller. Okay. We're going to run maybe 3 minutes long today. Our other measurement would be a voltage measurement. So consider instead this system. We just have our piezo element connected in parallel to some load capacitance and some resistance. And then here is our output voltage, and this could or likely would be chained into a voltage amplifier as well to make the size of the signal more easy to measure. Okay. So I have Some current I generated by the piezo element here. ICL. And IR like so. I can add all of those currents together. So that's going to look like IAC plus I motional plus ICL plus IR is equal to 0. The output voltage is just the voltage drop over the piezo resistor. So that's going to look like SC V out plus I motional plus SCL V out plus V out over R is equal to 0. And then rearranging things here, I'm going to get V out is equal to negative the motional current divided by 1 over R plus SC plus CL, which is the same as simply the motional current multiplied by our resistance in parallel with 1 over SC plus CL. At frequencies where omega is much greater than 1 over R times C plus CL, we get V out is approximately equal to negative I motional over SC plus CL, or negative EAS over C plus CL. Because our motional current is once again dependent on S, and so the S's are going to wind up canceling each other out. So in either particular case, we wind up getting an output signal that is proportional to the applied strength. All right, I am done talking because I've gone over the time that is allotted to me to teach this class, and also my throat hurts. I hope you guys have a good day off, just to be clear, because I have students in my Circuits 1 class that were not aware of this. Monday is a holiday and we do not have class. University is closed. So I will see you guys on Wednesday, where we will talk about something new, which I honestly don't know what it's going to be yet.